It's been a little while since I've seen some of you. I saw you guys on Thursday last week. We talked about the log, and then a lot of you were at the fatal distractions demonstration on Friday, so I didn't get a chance to see you. So really quickly, before we get into our actual notes, I'm just going to review like the idea of a log from last Thursday, so that we're all kind of like refreshed what is a log. And some of you, were at prom, so you're feeling tired. Okay, we need to review what is a log. First, we started off with logarithmic equations to help us understand the definition of a log. So I could write a logarithmic equation and say something like log base 3 of 9 equals 2. Okay. And so we had to like understand how do we say that, how is it written, but then really like what does it mean? Can anybody tell me what is log base 3 of 9 equals 2 in exponential form? What does it look like as a b to the x equals y? Kylie? Yeah, if we start at the base for the log, we use our switch method, we go around the equal sign to pick up the exponent 2, and then we set it equal to whatever we're taking the log of. Our exponential form is 3 squared equals 9, which helps us understand what a log actually means. It's finding the exponent that makes that true. 3 to what exponent is 9. Okay. So we can rewrite it, and we're going to use that rewriting method today, the swirl or the swoosh, where we go around the equal sign and back into the log. Then we applied it to problems like this, where instead of giving you the full equation, which you could just do the swoosh and rewrite and make sense of it, I took away the answer. So now I'm just going to say, here's an expression, log base 2 of 16. What is the answer? And remember, the answer to a logarithm is an exponent. Okay, so what you're trying to do is you're trying to figure out, what's the exponent to base 2 so that we get 16? Any ideas? What's the exponent we need? Damon? 4, yeah. So we can say log base 2 of 16 is equal to 4. And our reasoning would be, because if we rewrite it, this is my abbreviation for because, if we rewrite it, 2 to the 4th is 16. 2 times 2 is 4, times 2 is 8, times 2 is 16. Works out. So when you're evaluating logs, you're actually looking for the exponent that makes the exponential expression true. Reviewed a little bit for us? Okay. Now, what we're going to do today is, first we're going to talk about inverses, because inverses are going to be really helpful to graphing our logs. And finding inverses is actually something we did in first semester. So some of you may remember this from first semester, chapter 5. Okay. One of these a good example of how math always comes full circle and you always go back and do the things you already did with a new twist. That's what we're doing here. Here are your steps to finding an inverse. Number 1, the definition of an inverse mathematically is it's a function reflected over the line y equals x. So if y equals x, then you could substitute them in for each other. So in any math class, in any section or chapter, if you're asked to find an inverse, you can always switch x and y. And that could be switching x and y in an equation, switching x and y in a table, switching x and y on a graph from the ordered pairs. If you switch x and y, you're creating an inverse. Okay. We're going to look at it first from an equation perspective, and we're going to also solve for y then. So switching x and y is like the definition of a log, or definition of an inverse. Solving for y is what we're going to do to make our equation look like y equals. Make it look like y equals stuff. That's how we'll know we're done. So an important piece here, the piece that makes this chapter 6 material, and not the stuff we did in first semester, is exponents and logs undo each other. So a log undoes an exponential equation, and exponential expression undoes the log equation. Okay, so logs and exponents will undo each other. It's just like when we say, like, how do you undo subtraction? You add. How do you undo multiplication? You divide. How do you undo a square? You square root. How do you undo a log? You write it as an exponent. Okay, so they're going to undo each other. This means that when we're doing inverses, at some point we're going to have to rewrite it. Meaning we're going to have to do our definition of a logarithm in terms of an exponential equation and either rewrite it into log form or rewrite it into exponential form. So there has to be a rewrite at some point. And I like to use my little switch method to do my rewrite. Okay, so let's look at examples of writing in inverses, and then eventually we'll move on to graphing to help us. So we're going to find the inverse function of y equals 5 to the x. This function, as you see it, would you describe it as an exponential function or a logarithmic function? It is exponential. So I'm just going to make a note off to the side. This function is exponential, which means later on, when I find my inverse must be the opposite of an exponential function, which is a logarithmic function. So for some of us, when we have like trouble deciding, like in math, like what we're going to do or how we're going to start, I like to maybe take a step back from my whole like process and just say, if it starts out exponential, it ends up logarithmic. So I kind of know where my stuff is going to go. Now, going back to the notes we just took, the first step to finding an inverse is doing what? Switching x and y. So let's switch x and y in this equation right away. Now we're going to go through the process. Where I see y, I write x. Where I see x, I write y. And that's a superscripted exponent x. So I have a superscripted exponent y now. So I switch x and y. X equals 5 to the y. Your next job with this equation is to make it look like y equals something. Well, we're kind of at a weird place because y is up in this exponent. A lot of people might initially think about like dividing both sides by 5, but it's not 5 times y. So division doesn't undo this process. To get something out of the exponent, if it's trapped up in the exponent, rewrite it as a log. Okay, that's how you're going to break into that thing you can't get to. We can't get to y by our old methods of addition, subtraction, multiplication, or division. Because 5 to the y is none of those, so we have no inverse for it. This is exponential. So we're going to rewrite it. Okay, so at this step, we're going to rewrite as a log. When we rewrite it as a log, what will our base be? Log base. Which value here is the base to the exponent? 5. Okay, so we're going to start with log base 5. of, go around your equal sign, x equals the exponent y. And remember, that makes sense. The answer to the log is the exponent is y, so the log equals y. Have you just solved for y? Is y all by itself? Yeah. This is the inverse. Is the inverse a log function like we thought it would be? Yeah. So if we start with something exponential where there's a variable up in the exponent, we know that its inverse is going to turn into a log. Let's try another one. Does anybody have any questions before I leave this? Find the inverse function. We're going to find the inverse function for log base 1/8 of x. Okay, remember that you can take a step back from your problem. You can just look at it right at the very beginning. You notice this is what type of function? A logarithmic function, which means that when we find the inverse, we're going to have to switch it out of log form and into exponential form. So I know the inverse is exponential. So when I think about exponential, I think about like y equals b to the x. So I'm going to get rid of the log at some point. Before I do that, I have to follow step number 1 for finding an inverse, which is switch x and y. Everywhere you see y, right? X. Everywhere you see x, right? Y. It's to switch x and y. Oops, I wrote another x, 1. It is now your job to solve for y, but y is trapped inside of the log. In our previous example, y was trapped up in the exponent, and we couldn't do anything to get it out. Now it's trapped inside the log, and we can't do anything to get it out. We can't, like, divide by log base 1/8. That doesn't make sense. So when you're at this point and there's nothing to do, rewrite it. It's in log form. Rewrite it as an exponent. Remember that when you rewrite it in exponent form, you drop the log. Okay, so the log goes away. What is the base for your exponent now? 1/8, because you start at the base of the log. So we're going to say 1/8 raised to the x, always make sure you go around the equal sign to get your next piece, equals, go into the log y. Have you just solved for y? Yeah. So there's your inverse. Is your inverse equation an exponential equation? Yeah. This is nice for some people because a lot of times people will forget and they'll like still put a log in there. And so you'll see, like, if your first one has log and your second one has log, you know something's not written correctly because you shouldn't have a log in both. One should be logarithmic, one should be exponential. Any questions? Our inverses in chapter 6 are not going to get much more complicated than that. So like it should be really like a 2-step process. Switch x and y and rewrite it. Certainly we could have more extensive functions where there'd be like some other numbers that are added or subtracted, and then that would change as we solved for y. We'd have to add or subtract, multiply or divide those numbers too. But we're just not going to see that right now. Okay, so ours will be pretty quick and easy like these. Okay. Let's do some graphing so I can walk you through the steps. Oh yeah, let's do this one. Y equals log base 5 of x. I'll walk you through some steps to how you can graph a logarithmic function. It's going to be very similar to what we did for exponentials. There's a few key differences at the end when we're writing domain, range, and asymptote that you'll have to pay attention to. Okay, and of course the shapes will be similar but a little bit different. Okay, well the big issue with y equals log base 5 of x, if we were just to go straight into making a table of values, it would be really hard for us to pick x's that work. Like, if I did log base 5 of 2, I don't know what I have to raise 5 to so that I get the number 2, right? Because 5 to the first is 5 and 5 squared is 25. So that's a little bit hard for me. We don't have calculators right now that evaluate logs for us, so we're kind of at a place where we wouldn't necessarily be able to do a lot with a table. So we're going to break graphing into 2 steps. Step 1, find the inverse. So we're starting with a log function. Our inverse is going to be exponential. And we know how to make tables for exponential functions. That's easy for us to do. So we're going to find the inverse. Okay. To find the inverse, we're going to switch x and y. X equals log base 5 of y. You got to solve for y, but y is trapped inside the log, so now you're going to rewrite it. So you're going to say 5 to the x equals y. Questions on what I've done so far? Y equals 5 to the x is something that you could make a table for. We did that when we were graphing exponential growth and decay. So let's make a table of values right here. What numbers will we put in for x? What have we used previously with exponential functions? Negative 1, 0, 1, and 2. Yeah, so I'm not changing anything now. It's all the same stuff we were doing before, so this is a pretty easy process for us. If we do 5 to the negative 1, it flips to become 1/5. Remember, negative exponents don't make anything negative, they flip them. 5 to the 0 is 1. 5 to the first is 5, and 5 squared is 25. Now, if we were to graph these points, we would be graphing y equals 5 to the x, which is not our goal. Our goal is to graph y equals log base 5 of x. So step 2, is go back to log, okay? And what you did was you took a log, you found the inverse by switching x and y. We used the inverse to generate a table of values for x and y. But now we're going to switch the x and y in the table, and that gets us back to log. So you can switch x and y in equations, tables, graphs, and every time you switch x and y, you're switching forms. You're going to the inverse. So we'd be going back to logarithmic form. So all my x's become y's. All my y's become x's. Those are the points I'll graph. I switched it out of log form to easily make a table. I got to switch the table back to log by switching x and y. (1/5) negative 1. That's 1/5 to the right, which is not very much, and negative 1 down. 1, 0, 5, 1. That's all I'm going to graph. This is my graph of my log right here. And something very interesting that happens in exponential functions, our asymptote was always where? What's 0? Y equals 0. But in a log function, we've switched x and y, right? So what's our asymptote now? X equals 0. So x equals 0 is the y-axis. Now you'll always have an asymptote on the y-axis. And that changes things for domain, range, and asymptote. Okay, so if I'm listing domain, range, and asymptote, instead of y equals, it will now be x equals. Domain and range are always with the same variables. So domain is always talking about your x's, and range is always talking about your y's. So I went ahead and labeled them as x and y. But the domain and range from exponential functions are going to switch, and the domain for the exponential will be the range for the log function. The range for the exponential function will be the domain for the log function. So what was your domain in exponential functions previously? What do we always write? All real numbers for x, right? Well, that domain is now your range. So y will always equal all real numbers. That will always be the case for log function. The domain from exponential is now the range for log. The range for log used to be like y is greater than 0 or y is less than 0, depending on if they were above or below the asymptote. So now that's going to be our x's. X's are less than 0 or x's are greater than 0. These x's are greater than 0 because they're going to the right. So I just want to make this clear. The idea for domain and range switch, but domain is still x and range is still y. So this should read x is greater than 0, not y is greater than 0. I want to show you one other example of a log graph that has a fraction base, just so you can have two examples, because they have different sort of shapes. And then I'll give you your homework assignment, which is a worksheet. So one more example. I put this in your notes so you have an example of fraction base. The process is still going to be the same. Find the inverse. X equals log base 1/5 of y. So you switched x and y. You're going to rewrite it in exponential form. So that becomes 1/5 to the x equals y. Some of you might be catching on to a little pattern with rewriting or finding inverses, how they're connected. We're going to make a table of values with this equation that is exponential, using the same numbers we always have, -1 through 2. We have a fraction base, so when we flip it with the -1 exponent, it will become a regular number 5. 1/5 to the 0 will be 1. 1/5 to the first is 1/5, and 1/5 squared is 1/25. So those are getting smaller. Beware, do not graph this, because you will graph an exponential function. You must do step 2, which is switch it back. So you got to switch x and y in the table. 5, 1, 1/5, 1/25, -1, 0, 1, 2. those points. So 5, -1 is 5 to the right, 1 down. Oh, I'll use blue for the graph. 1, 0 is 1 to the right, 0 up or down. 1/5, 1, 1/25, 2. And you can see you're getting closer and closer to the y-axis, but you're not actually getting there. So now we're going up towards the y-axis instead of just coming down. So it's kind of like the flipped version if you compare it to your previous graph. You still have a asymptote at x equals 0 though, so that stays the same always, just like it did for us with our exponential functions. So we'll get domain, range, asymptote. Asymptote is always x equals 0. Range is always all real numbers. The domain, it could be on either side. Most of the time it'll be on the right side, so we'll say x is greater than 0 here. That's where we see the blue graph show up. Okay. So if you've been working on your exponential growth and decays, this really isn't too bad. The key pieces are you have to be able to write the inverse in the original part, and then you have to remember, of course, to switch it back. If it looks like all your graphs have horizontal asymptotes, that means you're probably not doing the second step of graphing, which is to switch your table. The reason we're using the inverse here is it's very difficult for us to evaluate logarithms unless they come out nicely with their exponents. So we want to use the inverse function because it's actually really easy for us to raise stuff to different numbers and then just switch those things.